Okay, let's try this again. All right, so in this example for class 18, this is example 1, I want to use a 4-bar and doing an acceleration analysis. Now, I originally wrote this problem and I wasn't thinking it through. I do want to compare it to Excel and to SolidWorks, and I have some difficulty in doing something, the acceleration, wherever I want to put an acceleration problem. So let's just keep it a little more straightforward and keep it as a constant velocity problem, but we'll look for the acceleration at point P. Now here are the situation here. We do a position analysis and we find what theta 3 and theta 4 are going to be equal to. Then we do a velocity analysis at that position for this the crank at 25 millimeters per second, radians per second, and we find what the angular velocities are going to be of the links 3 and 4. And now we want to do an acceleration analysis, and here are the equations were provided in Norton, and so it's a little bit of a pain to write these through, but with a little bit of work, it isn't going to be too terribly difficult. So we start marching through. We stick in 80 for C. Sine of 72, excuse me, the theta 4 is 72.30, so we get 76.21. B is going to be 120 sine 18.25, so we get 37.58. And then C, well, actually, while I'm here, let me go ahead and do a D, because they're very similar to each other. C and E are very similar to A and B, that is. And so that's the cosine of 72.30, and we get 24.32. And then E, we get 120 and cosine of 18.25. So we get 113.6. And for C now, start going through, we'll notice that we have a theta 2, excuse me, an alpha 2. And so because the alpha 2 is equal to 0, that's equal to 0. And then we go through the rest of it, and just it's going to be 40 times 25 squared cosine of 75 plus 120 times 0.4842 squared times the cosine of 18.25, and then minus 80 times 12.91. That's what we got there for theta 4, excuse me, omega 4. Getting things mixed up. I'm really tired of doing this, and you probably are tired of listening to them. And then we do the same thing for F. It's very similar. Got to watch out for our pluses and minuses here, though, because that's a minus, and that's 40.25 squared times the sine of 75. And then we have a minus here, right? So we got to be careful there. See, there's a minus versus the plus of our 120, 0.4842 squared sine of 18.25. And then last one, that's going to be a plus right there. So that goes 80, 12.91 squared sine of 72.3 something or other, 30. Okay, and so if we go for our alpha 3, right, we combine CD, AF, AE, and BD, right? So that quickly is, right, if I could do things quickly. Oh, by the way, I didn't solve what these were. I'm sorry. I should have put it in there. So C was equal to 2,442.7, and F is equal to negative 11,449. So our alpha 3 is going to be 2442.7 times D, which is 24.32, minus A, which is 76.21, times F, which is negative 11,449, all divided by A, which is 76.21, times E, which is 113.6, minus B, 37.58, times D, which is 24.32, and so we get 119.9. And for our purposes, this is actually all we really need, because we're trying to find the acceleration of point P, and we'll see that we don't need the acceleration, the angular acceleration of 4. But if we were to find it just for our own curiosity, you know, going through this equation up here, through the thing, and I'm not going to take the time to write the thing out. It's going to be 91.18 radians per second squared, and that'd be good. That's a thing that we can actually check from our Excel. And then if we want to find the acceleration of P, we do it by taking the acceleration of A and adding to it the acceleration of P with respect to A. So we can find the acceleration of A by going back and let's see, is it gonna do this for me? Sorry, let's see. I did all these things in the previous thing. Come on, there you go. So I accidentally wrote this. I didn't get rid of this thing from the previous version, but they give us the acceleration of A as an equation. We note that it's got two parts, and one of them is the angular acceleration contribution, which is going to be 0 for us. So we're only going to be left with this portion in each of them. And then they don't give us the acceleration of P with respect to A, but they do give us the acceleration of B with respect to A. And we could see the form of this. We know that if we wanted the acceleration of B, we would add the acceleration of B with respect to A. So we can find this acceleration of B with respect to A and use it because it's the same link, right? It's the coupler, but now it's got an extension. So instead of B, we use AP instead of B. And then we also use theta 3 plus del instead of theta 3, right? Because we, you know, on a 4 bar here, what we've done is we've just taken an extension off of this thing by AP long, and its del is the angle here. So here is theta 3 onto the thing. So if we want to get the acceleration here, we take the acceleration of A and we just combine it with the acceleration of this piece, but now we've replaced it with AP and the and these other parts right here. So if we want to get the acceleration of A in the x direction, that's going to be, well, that first part was 0, and then minus 40 is A, 25 is omega 2, cosine of theta 2 is 75. We end up with a negative 6,470.5. That's millimeters per second. Same thing with in the y direction. Except it's the sine, and we're left with negative 24,148. And these are both millimeters per second squared. It's a good idea to label stuff. And then if we wanted the AP with respect to A in the x direction, I said it was going to be AP, right? So it's going to be and it's going to be a minus, right, from the equation up above that I showed previously, was AP times theta 3, which we found to be 119.9, sine of theta 3 plus del is going to be 18.25 plus 15, 33.25. So it's going to be 33.25. And then you're going to have minus AP times omega 3 squared, or 0.4842 squared, and that's going to be times the cosine of 33.25, and that ends up equaling negative 9,890 millimeters per second squared. And very similarly for y, we end up with this one's positive 150, 119.9 cosine of 33.25, and this one still is minus, and that ends up being 0.4842 squared sine of 33.25, and we end up with a 15,020 millimeters per second squared. And it's therefore AP in the x direction is going to be negative 6,470.5 plus negative 9,890, and that ends up being negative 16,360 millimeters per second squared, and AP in the y direction is going to be negative 24,148 plus our 15,020 for a total of negative 9,127 millimeters per second squared. All right, so now what we would like to do is see what that happens in Excel, right? So we're going to end the show here. I'll keep this so I can refer back to it. I have to flip my screen, and the last time I did that, I shut the computer off and lost the recording. And I am such a busy guy, I do not need to be losing any more recordings and wasting my time by making the thing again and again and again. So the recording is 12 minutes long at this point. We'll go and do the Excel part of it. So I already did this. Let me take the, this is the one that I built the thing upon, right? So this is what I believe, this is what we had built last time, what we had constructed. We got to there, and we made we found the velocities. We also found the angular velocities of the 4-bar. All right, so let's go ahead and find the angular. Well, yes, okay. So everything here should be correct. Let's find the angular velocities so we can compare those. So I'm going to give them a label, and I'm going to call them. I'll put alpha 3 down in here, but we'll subscript this just to make it look nice and pretty. That's some of the Tennessee in me. And we'll do it for 4 as well. 4, boom. Yeah, it didn't want to, that's funny. It didn't decide to do the subscript here. And it's a waste of your video time that I'm still doing my subscript, but that's okay. Now for the acceleration, we need to skip down an additional level here and take this omega that comes after, divided by the minus the omega that comes before, divided by the time that comes. Let's see, make sure we get the right one. I believe it's going to be this one minus that one. Boom. And that's going to be the angular acceleration. And I'll do the same thing here, but this time I will reference these two cells. Boom. And while I'm at it, why don't I get my acceleration? And why didn't I subscript these guys? I don't know. They could have been subscripted too. I'm going to go A, and then I'll subscript. It looks better. A, boom, subscript. Oh, it just looks so much better. Okay, and so like I didn't keep that in my clip right there, but I'll grab this, and now this is going to be just 1 over. Yeah, that's fine. Okay, so that's going to be the time rate change of velocity in the x direction, and we'll do the same thing over here. This is going to be the time rate change of velocity in the y direction. Kaboom. And let's get rid of some of those decimal places, and I could just move them all down there. And let's check it out. Will it fit on the screen? See, here's the thing. You don't need some of these other numbers, right? They're all kind of squished up. So I can go ahead and hide some of these. Do I want to? Sure, I'll hide them, just so I could see the thing better. I'll give myself some more room. You might want to unhide them at another point. But right here is going to be our 75 degree, 70. Whoop, no, I don't want the text to be yellow. I want the blocks to be yellow so I could show it off. So I got 16,438, and I got negative, and I got negative 8,965. Okay, well, I'm showing the acceleration at the point. So how did I do right here? Let's take a look and paste it right in here. That ain't half bad. I would say that you're going to have like a propagation of error that's going to come in here. So if you had some error in the velocity, you're going to have even more error, I believe, in the acceleration. And we're getting towards class time, so I need to wrap it up. All right, so let's take a look. Also, while I'm there, okay, let me also come back and take a look at my angular acceleration here. We might want a couple more decimal places in this one. And let's go back to where we had the angular acceleration right here. You'll remember that this is what we found. Let's see, I just pasted it as something else that I didn't mean to. There you go. So here you go. We didn't do half bad. 119.9, we got 120.8. 91.18, we got 92.55. So it's looking like our numerical approach is pretty darn good. All right, so what I can also do is now I can go back into my SolidWorks, and for some reason I'm in the MATLAB right there. And let me see, did I do this one already? Oh, so I already did this one. I think this is the one, it's the same one. Because I did this a couple times, so I just want to see if, come on. All right, so yeah, this appears to be the right one. Let me get rid of this graph, if it'll let me. It's getting angry at me. It's mad at me now. Okay, don't be mad. Let me see. Hopefully I haven't bogged the thing down. It's telling me I haven't saved it in a while. That's fine. So now that it's already pre-made. You've already made this one. You've watched the other videos. All we need to do is to come in here and add another graph. So we go to acceleration, and we have linear acceleration, and we want the x component. And we'll go ahead and pick that little vertex. It picked it this time. We're going to create a new plot. Oh, by the way, you can show the vector in the window. All right, so that's kind of a nice thing to do, is to show that's going to be the magnitude of the x in that window, and you can see the graph of this acceleration. We'll take a look at the graph from the other method, and then we could do the same thing again for right here. We'll do in the y direction, take the acceleration, linear acceleration, and in the y component, and take a look at that. And I want to add this to the same plot. I'm only doing that so that it will, when I export it, it'll just be one file that I can look at. And I'll also put the vector on here in the y direction. I think that's going to. I think it'll show it. So let's put them in there. Like I said, I've shown maybe previously, we got to be a little careful. For whatever reason, there's some glitch. Take a look at the scale. That is not the correct scale. So what I've been doing is I come back to that. I go down to where that data is, come back into features. It just seems to be that if I just mess with something a little bit, when I click OK again, you can see that the scale now, yes, is correct in the Y direction. So it'll mess up the exported data too. So it's just something to be aware of. So I will export this graph right here to the spreadsheet, and it should open. Yep, it opens up another spreadsheet right here where I can grab the data and I could compare it to Excel, to the Excel result. I'm going to close this up because it doesn't like to play with too much stuff going on. But let's see if it'll also, when I come back up to here, let me edit this. No, I don't want to edit this feature, sorry. I want to expand this and edit the velocity. So edit this feature, and I want to show the vector on that one too. So that's the velocity vector that's on there. And let me see if it'll, well, it won't matter. I guess, will it? I think it'll just be the velocity vector. I don't think it'll be, yeah, it'll be fine. Okay, so it's showing you the magnitudes of the velocity vector. It doesn't have to be the x and y components. So when I play this right here, it's an interesting thing to look at the interactions between these accelerations, how they work and how they're moving along. I think it's a nice little visual thing, and I wish I could actually make this a little smaller. I think it's at 0.1 times the speed is as slow as it'll go, but it is an interesting thing to be checking out. So let me go and grab this, and I got to grab all of them so I can make a comparison. And I did 218 steps in this one, and I need to go back to my Excel where I have hopefully, actually when I move something, sometimes it gets rid of the thing in my queue. Let's hope it didn't do that this time. Nope, it allowed me. And I actually should have named this something different, so I kind of messed up by doing this. I think I'm gonna have to hit like undo 1,000 times. That's unfortunate because I wanted to keep and archive that that problem, but it's okay. I'll recreate it. It's just effort. That's no big deal. So anyway, let's see. Will it let me do this right here? It doesn't like to do that. I hate that. Okay. So anyway, I just want to see more decimal places so we can confirm right here is the answer or close to the answer according to Excel, right? So if we come back to here and compare this linear velocity that's right here, this is the terms that we're getting. And it's actually pretty close to our Excel results. These by hand results, actually. It's kind of interesting. I mean, the SolidWorks is pretty close to by hand. So that's an interesting comparison that we're able to make. We can also graph these two things against each other. We can put them on the same plot and check them out. Like we can, either way that we want to do. I think the best way to do it is to probably only do the X direction in the acceleration. Let's see. And we only need to come up to like that far and then do the acceleration right here. I'll hit control. Well, no, damn you. It's going to screw everything up. I'm wasting your time now. Oh, I don't want to go down that far. Damn! Why can't I be smooth? Why can't I be smooth? I'll go from here down to... get back up here. want to go down to only like right around here so far, and then do the same thing. It's got to be an easier way to do this. My mouse is getting sticky for some reason. I don't like that. And we're doing it in the X direction, right? So I'll come down in here. And by the way, we could also have graphed this, and I kind of think maybe I should have been. You know, I think some of these things are already like complex enough without the homework assignments confusing enough with the stuff I haven't added in there. But I totally could have just plotted out the other like the solutions based damn it, I hate zooming at the solutions. From equations, I could also put those into this right here as more columns, and so we could analyze those and how close they came instead of just looking at the individual thing that we calculated at 75 degrees we calculated by hand. But let me add in what we had for the SolidWorks here. And whoa, what happened here? Oh, I guess. Oh, I know the numbers. All right, come on down. All right, so you're making me mad, kid. So I'm just gonna copy and paste you over here, and the thing I want to get is in cell AB. So I want to change that to B, and that to B, and I think I should be okay. And boy, they land right on top of each other. Ooh, boy, that's pretty good. I like it. That is pretty cool. And, you know, like you're going to format these things as we have before. Something I think I neglected to tell you is you should turn the smooth line off. I think it can distort and give you a sense of the refinement or be misleading. And I'll turn this one into the dashed, and then I'll grab the other one. Let's see, grab the other series right here. Do the same thing. Turn his smooth off, and reduce his thing. And now we could zoom in there. We could see some of the differences. There's definitely going to be some differences in the time steps. As we go through in here. But I've shown you this before, and the video is getting too long, and class time is coming up. So I want you to make sure that you format the graphs so that we can so that they're usable. And let's see, we'll take this and make him go from 0.2 to 0.25. And zoom in there, and you can kind of see now we can see some of the differences, right? These are the points that are actually being plotted out, and you can see now that the smoothing of this thing is kind of artificial, right? It's painting you a picture to make it when you put the smooth on, that makes it look like it's much more refined than it is. Even though it's not a pretty thing, if you're trying to do some analysis, you're trying to discuss it, it's better to turn the smooth off. So that's my 28-minute video for that example. And hopefully we'll be able to do this in class without it being quite so long. See you soon.